In this lecture, we look at few examples of calculating the Fourier transform for some important signals that we see in experimental science. And based on these examples, we look at the uncertainty principle. In the previous lecture, we have seen that for a function f of t, the Fourier transform is defined by this integral and the inverse of this, that is the inverse Fourier transform, is defined by this particular integral. So in these lectures, we'll denote the function of which we are computing the Fourier transform as f of t, and the Fourier transform by capital F of omega. Omega is the frequency. Another way to denote the Fourier transform is using this notation, and the inverse Fourier transform can be denoted as this. The Fourier transform is particularly important in experimental science because usually a temporal signal such as f of t can also be a spatially varying function. In that case, we'll have function, let's say f of x, and most of the times such functions in space or time are difficult to visualize in the time domain or the spatial domain, but they are easy to visualize in the frequency domain. So the Fourier transform allows us to represent this function in time domain in the frequency domain, and this function is said to be defined in the time domain. Also, many signal analysis techniques such as filtering, cross correlation, and the response of instruments to input signals are easier understood in the frequency domain rather than in the time or the spatial domain. So we'll discuss the applications of the Fourier transform in experiments later in detail, but in this lecture we'll look at few examples of how to compute the Fourier transform. Before we look at these examples, first it is important to look at the conditions for existence of the Fourier transform. The only requirement for a function f of t defined in the time domain so that its Fourier transform exists is that the function should be absolutely integrable. That means that this integral of the absolute value of the function is finite. Note that in our case, we'll always be dealing with a real valued function. So this notation denotes the absolute value of the function. And this particular condition, that the function is absolutely integrable, is true for any experimental data because this data is taken usually for a finite time period and the values of f are also finite at all these times. So therefore this integral is also finite. However, this particular condition limits the class of functions for which the Fourier transform exists. And for example, the Fourier transform of a harmonic function f of t equals to a times sine, let's say, omega naught t, and this function defined over the infinite time axis, the Fourier transform for such a function does not exist. In the classical sense, the Fourier transform for such non-integrable infinite signals can be evaluated in terms of the generalized functions such as the Dirac delta function, and we'll discuss this issue later on, how to represent the Fourier transform of non-integrable signals. Now, let us look at a few examples for which the Fourier transform exists, that is, these functions are absolutely integrable. And the first example is the Fourier transform of a rectangular pulse. So this is our original example using which we motivated the Fourier transform, and we saw how we transition from Fourier series to Fourier transform. Now let us consider this pulse of time duration a, and this pulse is of rectangular shape and the amplitude is capital A. So this function can be defined as a within the time interval minus a by 2 to a by 2 and 0 for all other values of time. The Fourier transform for this function is given by this integral, and because f of t takes a constant value between this interval minus a by 2 to a by 2, we can write this integral as the constant value capital A times e to power minus iota omega t dt. When we compute the Fourier transform, we integrate over time, and therefore we get a function that is a function of the frequency omega. So we go from time domain to the frequency domain. Now let's carry on this integration. So we have minus a over iota omega e to power minus iota omega t, and the limits of time t are between minus a by 2 to a by 2, and this is equal to a over iota omega e to power iota omega a by 2 minus e to power minus iota omega a by 2. Alternatively, we can write this as a times sine omega a by 2 over omega by 2. Another way to write it is to divide by the duration of the pulse a, and we get this form of the Fourier transform. We'll see throughout the discussion on Fourier transforms that a function like this That is, let's say function f of x equals to sine x over x appears so often in our discussion on Fourier transforms and signal analysis that it has a special name, and that name is sinc. And this function is called sinc function. And note that by the virtue of the famous limit x tending to 0 of sine x over x is equal to 1. So the Fourier transform for a rectangular pulse of amplitude a and duration small a is given by this function. Now let's look at the plot of the Fourier transform of a rectangular pulse. So here is the plot of the Fourier transform of the rectangular pulse. So first we see that the peak value is capital A times A, and then we have the sine function, but as we go away from the origin, its amplitude decreases by 1 over omega. So the amplitude of the sine wave goes down, and therefore we'll get a plot something like this. So the first crossing of this function at 0 is at 2 pi over a, and this function is also symmetric about the vertical axis. So this is 4 pi over a. Similarly, on the negative axis. There are two things to note about the plot of this Fourier transform. So the first thing to note that is the value of capital F of omega, that is Fourier transform of the rectangular pulse at omega equals to 0, that is f of 0 is a times the amplitude times the width. That means this is equal to the area under the curve in time domain. And that's not a surprise, because if we substitute omega equals to 0 in the definition of the Fourier transform, so we'll not have this particular term, and therefore we'll see that we are left with an integral of the function over the whole time domain minus infinity to infinity, and that corresponds to the area under the curve. So this particular value at omega equals to 0 will always correspond to the area under the curve for the function defined in the time domain. And this is not something specific to this rectangular pulse. It holds for any function, as you can see from this particular integral. Another thing to note is that the pulse duration of this function is a in time domain. However, if you look at this particular plot over here, we see that the width of the Fourier transform in frequency domain scales as 1 over a, that is the inverse of the duration of the pulse in time domain. So that suggests that if I make this pulse wider or broader in time domain, this particular Fourier transform will become narrow in frequency domain. And we'll see that such kind of behavior is a characteristic of the Fourier transform, and we'll discuss this through examples of other signals. Now, let's look at Fourier transform of an exponentially decaying signal shown in this curve. So the function in time domain is given by this plot, that on the negative time axis the function takes on 0 value, whereas on the positive time axis the function is an exponentially decaying function given by capital A, which is this particular value at t equals to 0, times e to power minus at. That is, the function is given by 0 for all times less than 0, and is given by a times e to power minus at for time greater than equal to 0. And this constant a we'll consider to be greater than 0. So a is actually the rate at which this exponential signal decays, or in other words, the time scale for the signal to decay is 1 over a. That means the width of this signal in time domain scales as 1 over a. In this particular case, even though the signal extends to infinity, its integral of the absolute value is finite. That means this integral is finite. That implies that in this particular case that the area under this curve is finite. So now let's look at the Fourier transform of this function. So we have the Fourier transform f of omega is given by this particular integral because the function is 0 for all values of time less than 0. So we'll have an integral over 0 to infinity, and over this time interval the function takes on a value of e to power minus at, and then we have product with this complex exponential, and we can alternatively write this as a times integral 0 to infinity e to power minus a plus iota omega t dt. This integral is easy to compute, so we'll have a over a plus iota omega with a negative sign, and then we have this term, and the limits are from t goes from 0 to infinity, and as t tends to infinity this tends to 0, so the Fourier transform is given by capital A, that is the amplitude over here, divided by A plus iota omega, which can alternatively be written as this. One thing to note is that in this case of an exponentially decaying signal, the Fourier transform is complex valued, in contrast to what we've seen for a rectangular pulse. In general, Fourier transforms are complex valued, but as we have seen for Fourier series, the Fourier transform is real valued only if we have a real valued function that is also even. So in this particular case, our function is not even, although it is real valued. So we have a complex valued Fourier transform. And we have seen that for a rectangular pulse, the function is again real valued, but also an even function. Therefore, the Fourier transform of a rectangular pulse was real valued. Now, let's look at the plot of the Fourier transform of the exponentially decaying signal. So note that because the Fourier transform is complex valued, we cannot plot it directly. So we'll plot the magnitude of this Fourier transform of the exponentially decaying signal. And the magnitude of the Fourier transform is A over under root A squared plus omega squared. So this plot will have a peak value that is at omega equals to 0, that is, and this value is at omega equals to 0. And again, one can check that this particular value, capital A by A, is in fact the area under this curve. The magnitude of the Fourier transform is symmetric and it decays with omega. The Fourier transform looks something like this. So note that in time domain, the exponentially decaying function has a width that scales as 1 over a, whereas in frequency domain, if we represent this function using the Fourier transform, then the width of this function given over here scales as a, because let's say we want the full width at half max, that means the width of this function, so that this function has half of its peak value, then this would occur at values of omega that are under root 3 times a and minus under root 3 times a. So we can see that width of this Fourier transform scales as a, in contrast to the function in time domain where the width of the function scales as 1 over a. So again, we have a reciprocal relationship between the characteristic width of the signal in time domain and that in the frequency domain. Next, let us look at the Fourier transform of another important function, that is a Gaussian function. In particular, let's consider a normalized Gaussian function given by this, which is defined on the infinite time axis. This is the similar function by which we describe the normal distribution. So here is the plot of this normalized Gaussian function. By normalized, we mean that the area under this curve is equal to 1. The Fourier transform for this function is given by this integral. To solve this integral, we can write the integral in this particular form. As this. Here we have added and subtracted these particular terms because that allow us to complete the squares. That means this integral can be written as so we'll take this particular term as a separate term, which is given by exponential of minus sigma squared omega squared over 2, and we have another exponential term as this. Now note that our integral is over time, not over the frequency omega. So we can take this term outside. That means we can write this particular integral as this. Now, if we substitute this t plus iota sigma squared omega as another variable xi, then we'll see that this can be written as which along with this particular term is a Gaussian. That means f of omega, that is the Fourier transform, can be written as exponential of minus this thing. As this, where we have assumed that the imaginary part makes no difference to the limits of this integration. And again, we see that this is an integral of a normalized Gaussian and therefore it is equal to 1. The final result, therefore, is that the Fourier transform of a normalized Gaussian with standard deviation sigma is given by this. And this function is itself another Gaussian, but with a different standard deviation or the width. So let's look at the plot of our original function and its Fourier transform. So our original function was this. The plot of the function in time domain looks something like this, where the width of this function, the characteristic width of this function, scales as this sigma, which is the standard deviation of the Gaussian normal distribution. And similarly, this function also has the width which scales as sigma. On the other hand, if we look at the Fourier transform, and note that this is another Gaussian, although it is not normalized, but this function can be written like this. So we see that this is a Gaussian with standard deviation 1 by sigma. And now that we are familiar with our Fourier transform, even without looking at this function, we can tell that this particular peak has a value of 1 because the area under the curve in time domain is 1. And the width of the Fourier transform scales as 1 over sigma, again, which is the reciprocal of the characteristic width of the function in time domain. From all these examples of the rectangular pulse, of an exponentially decaying signal, and the Gaussian function, we have seen a particular feature that the width of the function in time or the spatial domain is inversely related to the representation of that function in frequency domain, that is the Fourier transform in the frequency domain. In other words, if my pulse duration increases, then the width of the signal in the frequency domain shrinks down. And the width of the signal in frequency domain is actually called the bandwidth. So if the pulse duration increases, the bandwidth decreases, or the vice versa. So the pulse duration and the band width are inversely related to each other. So here, this is the pulse width or the pulse duration, and this is my bandwidth. So note that in this particular case, the function extends from minus infinity to infinity, but by duration we mean the characteristic width of this signal. That means the width over which this signal attains some particular value, let's say 0.1 times the peak value. Similarly, over here we can define bandwidth something like the values of frequency for which the value of the Fourier transform or the magnitude of the Fourier transform is 0.1 times the peak value. Now let's go back to our Fourier transforms of the various examples that we've seen and look into more detail of how the pulse duration and bandwidth are related to each other. So in the case of a rectangular pulse, my pulse width is exactly equal to a because the function is 0 at all other time intervals outside minus a by 2 to a by 2. So we can say the pulse width denoted by delta t is equal to a. And the bandwidth we can define as, in this case, as the width corresponding to frequencies at which this function attains 0 value for the first time. So that means in this case we have this width is 4 pi over a. So my bandwidth I can say is delta omega equals to 4 pi over a. Therefore, for a rectangular pulse, the product of the pulse width and the bandwidth is given by 4 pi. Similarly, for an exponentially decaying signal, I can take the pulse duration as 2 times the characteristic time scale of the exponential decay. So let's say that we take delta t as 2 over a. So at this particular time 2 over a, the function attains a small value that is given by e to power minus 2 times the peak value a. And the bandwidth for this Fourier transform shown over here, let's say we take delta omega is twice the value of that particular frequency for which the magnitude of the Fourier transform is 0.1 times the maximum value, in which in this case is, so that value if we see is given by, let's say, a squared plus omega star squared, and we want that value of omega that is 0.1 times capital A over A, and this gives us omega star is under root of 99A, or approximately 10 times A. So the bandwidth, which is twice this value of frequency, is about 20 times A. So therefore, for an exponentially decaying signal, my pulse width is 2 over A, whereas my bandwidth is 20 times A. Therefore, the product delta t times delta omega is another constant that is independent of the rate of decay of this exponential signal. That means if I had another exponentially decaying signal with a different rate, still the product of the pulse duration and the bandwidth would be a number that is independent of the characteristic time scale of the decay of the exponential signal. Finally, for the Gaussian function, we can take my pulse duration as, so this width is about 2 standard deviations, so 2 sigma. So the pulse width over here from minus 2 sigma to 2 sigma is 4 times sigma. And because my Fourier transform of a Gaussian is another Gaussian but with reciprocal standard deviation, therefore delta omega is given by 4 over sigma. That means the product of the pulse duration and the bandwidth is, in this particular case, equal to 16. Again, in this example, if I have another Gaussian with a different standard deviation, again the product of the pulse duration and the bandwidth would be a constant number that does not depend upon the standard deviation. From these examples, we have seen that the pulse duration and the bandwidth are inversely related, and also that delta t times delta omega by, let's say, 2 pi is always a number that is of order 1. So this relation between the pulse duration and the bandwidth is called the uncertainty principle. So this uncertainty principle is of significant importance to experimental science, because what it suggests is that if we wish to find a particular frequency at which a physical variable is varying in an experiment and we want to do it with more accuracy, that means we want to have better and better precision by which we want to know a particular frequency in that signal. So delta omega should be small, and that means I need to acquire signal for a longer duration. So the uncertainty principle says that if you want to have a Fourier transform that is narrow, then you need to have a signal that is broader in time domain. And if you have a signal that is narrow in time domain, then the Fourier transform of that signal would be broad in the frequency domain. Most of you would have heard of the uncertainty principle in the context of quantum mechanics, and there it is called the Heisenberg's uncertainty principle. The Heisenberg's uncertainty principle is in fact the same uncertainty principle for the Fourier transform. So the idea is that if we represent a quantum object with, let's say, some waveform in space, then we can alternatively represent that waveform in the wave number domain. For a spatially varying signal, the frequency is the inverse of the wavelength, that is the wave number. So let's say that this function, if it is defined by the Fourier transform in the wave number domain, and let's say that it is represented by some other curve in the wave number domain or the frequency domain, then the point to note is that the momentum is related to the wave number by the Planck's constant divided by a factor of 2 pi. So in fact I can say that this representation or the Fourier transform is in the momentum domain. So a waveform that can be represented in a spatial domain like this can alternatively be represented in the momentum domain or the wave number domain. And now we can see that the width of this waveform delta x would be inversely related to the width of the Fourier transform of this wave function in the wave number domain or the momentum domain. And therefore, in quantum mechanics, we have delta x times delta p is equal to a constant. So this Heisenberg's uncertainty principle also follows from the uncertainty principle of the Fourier transform. In this lecture, we have seen Fourier transforms for three signals, and we've seen some common characteristics of the Fourier transforms of these signals. The signals that we have seen in this lecture are those which are absolutely integrable, and that is this particular integral is finite. In the next lecture, we'll see how we can define the Fourier transform for non-integrable signals in terms of generalized functions.